Well, hello everybody. Thank you for coming to this presentation. My name is Boriss Mejias. I'm a solutions architect at EDB. And the story that we are going to see is not the typical presentation with the slides and bullet points. This one is a storytelling. So it's a different format. And we were going to go together with Monica DeBea, a tremendously talented support engineer who is going to investigate together with Kevin and Derk about a problem that Derk has with his project with synchronous replication. So we are going to go step by step until we find a solution to Derk's problem. All right. So this talk is called What is Going On with Synchronous Replication? And my name is Boriss Mejias. I work at EDB. And I'm not just doing this presentation on my own. I have a super big help from two persons that I really appreciate and admire a lot. One of them is Derk van Veen, who works at Adyen, and he's going to be coming with a problem which Monica DeBea is going to try to help him to solve. Now, the illustrations are done a little bit by me, but huge part is done by Scarlett Riggs. So shout out to her for her tremendous work with these illustrations. Now, let me tell you what this story is about. If you have heard before about Monica DeBea, maybe, she's a very talented support engineer that has to work in the office because the boss doesn't give her enough confidence to work from home most of the time. So she was really at the end of the day, and she was kind of waiting that everybody was going to go home because everybody was kind of tired to do anything else, while she was still monitoring everything in her system. She was looking for new problems because she's really motivated. Now, at a certain point, their phone started to ring again. And when the phone rang at that time, she's always expecting David. David is a very kind of careless developer who kind of break things at the wrong moment, and then he always blamed the database. So that's why he calls her all the time at that time. But in this case, it wasn't David. It was a more interesting problem, somebody who investigated the stuff more carefully and came up with something really straightforward to investigate. This was Derk, that software engineer that is always carrying his chessboard and ready to challenge absolutely everybody to play a chess of game. So Monica picked up the phone and said her usual sentence, Postgres support team, have you tried turning it off and on again?
Hi, Monica. I did not. Derek here from the Rapid project. I just sent you an email.
Hi, Derk from the Rapid project. So are you calling me just to tell me that you sent me an email?
No, I hate people who do that. But it's the end of the day, and I wanted you to know if you have some time tomorrow so we can meet in person so I can explain a kind of difficult problem to you.
Well, that will depend on what the problem is about.
Well, we have significant job delays, and it seems to be related to a large amount of SyncRep wait events. And we observed the same delay in synchronous replication in both replicas. They seem to be correlated with vacuum on large tables and with checkpoints, but you will not really like this, but terminating the vacuum process really helps in this case.
Yeah, well, indeed. I don't like when people terminate vacuum processes.
Well, that's why we need your help. I attached some graphs to this email.
Some graph. Okay, let me check that. So there from the Rapid project, you sent me some graph with some problems with the sync replication, and you sent me a picture of a boa constrictor digesting an elephant.
I sent you what?
You sent me an elephant being eaten by a serpent.
I have no clue what you're talking about, but there is a graph with the amount of SyncRep wait events measured on the primary server, and it suddenly spikes and to above roughly 400, and then suddenly drops again to near zero. Is that what you're talking about?
Oh, okay, I see. Well, okay. Yeah, this is interesting indeed. Okay, let's meet tomorrow after lunch. That seems like a good idea.
Right, cool.
Okay, so by the way, before you go, you know that the Rapid servers are not yet included in our monitoring dashboard, do you?
Yeah, I know, but I sent you the reference to all of our servers, so you can connect to them if you want to investigate directly on the servers.
Okay, that's very good. Excellent. Okay, see you tomorrow then.
All right. Should I bring my chessboard?
Okay, well, bring it. We will see if we can play.
Great. Sounds good. See you tomorrow.
Okay, good. Thank you, Derk. All right. So Monica was with this problem, very well explained by Derk, already wide investigated, not just something like, the database is slow, just go ahead and figure it out. That's how you have to provide information to the support engineer so that they can really help you. All right. So Monica was confronted with this problem now. She started to think immediately. She set up some stuff in the servers that Derk sent to monitor, and then she was ready the next day to discuss with Kevin. Kevin is the other engineer who is trying to learn from Monica as much as he can. And every time that the two of them solve something together, Kevin, for some reason, gets all the flowers and the promotions from the boss. And Monica always has to stay in the back for some reason. Anyway, when they were started to discuss, they started to talk about synchronous replication. So Monica wanted to explain Kevin what the problem was, but Kevin, in his wheel of learning, he said, like, can you explain me again how synchronous replication works? You did it already, but I want to see whether I remember stuff and see where the problem could go. Okay, said Monica, perfect. Remember, we have the database, which is just files somewhere in a disk, but you need to access them through the memory or the RAM. So whenever a service starts to read something in the database, there's going to be a piece of the file that is going to go into the memory so that that information can be read. And that is the cache of the system, the shared buffers. It is shared because if some other process accesses the same data, it just reads the data that is there immediately. Now, this is just reading. Whenever you write something, you're going to make that buffer dirty. And that buffer that is dirty doesn't go immediately to the disk where the file is because that would be too slow. So we brought Postgres put it into a write-ahead log, which can also be seen as a append string of changes. Yeah, so you're always putting all the changes so that whenever something goes wrong, you can replay all those changes and you always get a consistent view of your database. And because you can replay that stream of changes in the write-ahead log file, that is what you can be used for replication. Whether it's synchronous or asynchronous, there is going to be another machine at the other side which is going to receive this stream of changes, which are being sent by a process called the wall sender, because it's sending the wall files, and it sends it to the wall receiver. When the wall receiver gets that information, the first thing that it's going to do is put it from the memory to the disk, because the disk is your durable storage. So it's going to send that directly to a wall file again. So from a wall file through the wall sender, the receiver, to another wall file at the replica. Now, it's not enough to just send it to the wall file because this is done through the file system. And the file system is going to put it in some cache, whatever the system works. You want to be really sure that it's going to be on disk. So if something crashes, it is durable storage. So that's why you have this final loop, which is you're flashing into disk. Yeah, that's two different things. One is to write to the file system, and then from the file system, read physically on disk. Then, of course, you can put that particular buffer into the piece of block of data into the shared buffers, and it's accessible at the replica as well. But this is secondary. The thing is that it's already on the disk at the replica. Now, that writing loop also happens locally. It's not just in the replica, but it's also locally. So this is everywhere in all the systems that are running Postgres. So that's replication. Now let's see synchronous replication. And in the same drawing, I'm going to add some green arrows so that we can get the idea. When a process says commit this transaction, that commit will go all the way down to the WAL file, and it's going to be also written directly to disk, and then it's going to be sent, because it's reading the WAL sender, everything to the replica. Normally, if it is asynchronous replication, you can immediately tell the process it's done. We have it on disk here. We're going to do all the other stuff in the background. But in this case, because it's synchronous replication, you want to prevent data loss, as in the Rapid project, and you want to do it fast. You want the replica to acknowledge that it already sent information to the disk. So what you usually do is that when you send, well, not you, it's the Postgres service, when you send that message to the replica, there is a wait event called SyncRep. And that is the wait event that Derk is saying that is go to about 400. So there are 400 commit transactions that are waiting for that SyncRep to come back from the replica. And then Kevin says, okay, it's all good, but slow down. So you have this SyncRep, which is waiting. At which moment does it return back? Immediately when it receives it? Oh, Okay, let's see. There are two possible points, actually three. When you send it to the disk, it says like it is a remote write because it's written to the file system. But if you say that it's really synchronously on, it is when you put it back on the disk immediately and it's physically on the disk. If you have more than one synchronous replica, which is recommended, you're going to get it from the file system to the physical disk. So you don't really have to wait too much for that one. And you can take a little bit of risk. And then as soon as you get the file system telling you that it got that commit, then you can reply back as it is drawing here with the green arrows. At that moment, when the SyncRep gets acknowledged, it disappears from the wait events. And when it disappears, it means that we can confirm to the other process that the commit is fine. And the application is happy because the data is in at least two places. Okay, so that's the synchronous replication. So we need to understand why there is an accumulation of synchronous replica at a certain moment. All right, Kevin says, this is the point. What could be the file system, could be the disk, but I don't think there is that because we have very good disk. This is SSD, is as fast as we can go. It might be the network. So they started to investigate. And they said, okay, we look at the picture, we see all the possible arrows. Let's start investigating the possible root causes of this. When another process sends a commit, another commit, and it's going to have another SyncRep, that could be the network. Yes, we can investigate that. So they look at the network, they look at the values that Monica puts monitoring the day after. It was not the network. The network was super fast, no problem there. Then they continue looking then at the CPU consumption. The CPU consumption could have been an issue, but in this case, it was not. So carry on looking at the RAM. RAM consumption was okay. The amount of free RAM that you had available, it was enough to store the latest release of Thundermother without any problem. And then they look at the disk then, but the errors were like kind of not exposed to a lot of usage. There was something in between there that was causing this problem. So none of the usual suspect was there. At that time, it was remembered by Monica upon the question from Kevin that there was some issue with the vacuum, some correlation with the vacuum. So they continue investigating. So these commits that are accumulating the synchronous replication there is not the only thing that is sending data to the other side. There are some processes like vacuum that needs to load tables in order to clean them up. And this is going to generate more WAL files. And those WAL files have to be sent to the other side, creating a lot of WAL when the vacuum process a table which is very, very large. When we say very large, we're not talking about gigabytes, we're talking about terabytes. So that's something to consider. So although this was not part of the commit messages, it was generating a lot of WAL files. And this was being sent through the same process of the WAL sender to the WAL receiver, generating more WAL files at the other side. And when you have too many WAL files, you reach the threshold of the maximum WAL size, which is going to trigger a checkpoint, which means that more I/O going from the shared buffers to the disk in order to write all the data that is in the buffers. And that produces a restart point at the replica. So whole a concatenation of things. So might be something there. All right. So when you send that message to the disk, it is already a lot of accumulation of WAL files. So the synchronous replication starts to accumulate. They go beyond the 400 and then more and more. And then you get this problem that Derk is super worried about. All right. This is the graph. This is why this is being observed. We just don't know why. Okay, so Kevin, we need to talk to Derk again because he's coming after lunch. Yes, but we first need coffee, said Monica, very wisely. At that moment, Derk arrived in the office. They didn't have so many good news. Hey, Derk from the Rapid project. You were right. This is indeed a very interesting problem. And thanks for all the information that you already sent via email. It's a very good investigation so far, what we have observed.
Yeah, thanks a lot for the compliment, but we are still very puzzled with what we see.
We are puzzled too. Actually, we had to look at the RAM consumption, CPU usage, even the storage, which is SSD. I mean, this is bare metal. It's the fastest thing that you can get. I mean, but the serious problem is there. So we look at the network, of course, the first Nothing is a problem. So no usual suspect is having the problems.
Okay, but there definitely is a problem. So do you have any clue what could be causing this huge amounts of wait events?
We will continue investigating what you said about the correlation with vacuum and checkpoints. So we don't know yet. We will investigate more. So let's meet on Friday.
Well, if we have little to discuss now, sounds good to me. And as this meeting fell short, shall we play some chess?
Okay. Although I'm telling you the story, I don't know all the details, so I don't know actually whether they played chess at that moment on the Tuesday. What I know is that Monica and Kevin were really puzzled about this particular problem. So they continue investigating why did they have these wait events. They were waiting and accumulating and waiting even more. What was going on? So they get back to this problem. And they started to see, okay, there is something when you are writing the synchronous message from the word receiver down to the file system that is causing some trouble there. So they decided to zoom into that particular moment when there is a lot of WAL files and a lot of restart point happening at the same time in all the replicas, because this is something consistent across the replicas. You always want to have at least 2 replicas if you want to do synchronous replication. Yep. So they decided to look at the WAL receiver process, and they investigated it with 2 particularly useful tools. SS for statistics of the sockets, because the network is actually files where you're writing those sockets, and then it's going to produce an input and an output. And also with perf, where they can see what are the events that a process is waiting for. And then they observed that when the buffer of the word receiver was being accumulated, there was a switch into what they were waiting for. So when you are writing stuff to disk, that's a certain operation. But then when you're waiting for the disk to be flashed, that's an operation called the F data sync. That's a normal thing that you have to wait more, because physically writing takes more time than just writing to the file system. But in this case, when that buffer was full, there was a switch to the pwrite64, which is actually just writing into the file system. So it wasn't really the disk, it was the file system the problem. They look at network, RAM, CPU, disk, but it was a file system. They said, why would it be the file system? Said Kevin. We are just generating a lot of files. Let's get more coffee before we continue investigating, because there's too much things to investigate. All right. So what's happening with those WAL files then, said Kevin, because there's too many of them. Well, whenever there are checkpoints, there is the archiving that happens as well afterwards. Like saying like, okay, we already wrote all these WAL files, so we can get rid of some of them, and then we archive them, but you don't just delete them, you reuse them. Does that mean an operation in the file system just to rename a file? And apparently, for some reason, something that should be super fast is taking a little bit of more time when there are so many WAL files. So that could be an issue. So, okay, so Kevin, can we do something about this recycling of the WAL files? Yeah, well, there is a parameter called WAL recycle. Maybe we should disable this. That should be safe. Okay, what else? So whenever you have to create more WAL files, what you want to have, the reason why you reuse them is because you want to have a certain amount of disk, 16 megabytes, all in the same place. You don't want to start creating new pieces of 16 megabytes because it could be split into 2 and 4, and then 8, or then 2 pieces 8, or you just want to have the 16 in all one single place. So what Postgres does is whenever you want to create a new WAL file, it adds zeros on it so that you immediately reserve the entire stuff. It's like when you want to have a drink with your friends in a pub, you immediately put your jackets in all the chairs so nobody else pick up that table. And everybody then can arrive afterwards and pick up the chairs. Now, that pre-process, before you sit, that you have to put a preparation for the table, that also takes time on the file system. Can we do something about it? Yes, there is a parameter called the WAL init 0. That is the one that says like initialize the file with zeros. Maybe with the amount of WAL that they're generating, you don't need to prepare anything. You just write the whole thing. Said Monica. Then WAL recycle, WAL init 0. This gives me an idea. Let's just disable these 2 things. Let's go and talk to Derk. Derk, come. It was Friday. Derk arrived. A little bit tired for the very busy week. But then it was time to talk to him. Derk, so here's our hypothesis. We believe that all this thing, as you were saying, it is really associated to vacuum and checkpoint. And when the large tables that gets vacuumed, there is a huge amount of WAL file that is generated. And I must admit that I haven't seen this amount of volumes of WAL before. I mean, this is an 18 terabytes table. I mean, shouldn't we be considering partitioning the table?
Yeah, we know it's in our roadmap, and we will partition this table in our as part of our next large upgrade, which is scheduled for next quarter.
Okay, good. So partition your tables. Too much WAL. And because there is so much WAL, when this vacuum process starts, the threshold of max WAL size is immediately reached. This triggers checkpoints.
Yeah, we already increased the max WAL size a few times.
Yeah, we saw that the value is already large enough. So we are not going to plan to change that value. But there are other things that we want to do. Because when the checkpoint starts, it is going to clean up WAL files. And by cleaning up those WAL files generated by the vacuum, all this stuff is going to delay the writing of new WAL file. And because it's delaying that thing, when the synchronous flag arrives, it cannot immediately start writing, so that delays the process of the SyncRep. And the primary stays there waiting for those SyncRep because the system just cannot write.
Okay, I'm following you, but is there a suggestion in this?
Yes. We want the system to write as fast as possible. So we don't want anything to prevent that preparing chunks of 16 megabytes or whatever. So we know that this is a value that normally works in every system. It's an average workload, but you don't have an average workload. Your WAL rate is super large. So what we suggest is disabling this WAL init 0 that prepares the file to be one single chunk, and to disable the WAL recycle of file. So this might be the two changes that we want, but definitely the WAL init 0 might be the most relevant change that we want to apply. What do you think?
Well, it's definitely something we didn't consider at all.
Okay, good. Yeah, we never considered that either. So, but this is a really special case. Okay, so let's do that. Let's change the WAL recycle and the WAL init 0.
Yeah, let's do it right now. It's Friday, end of the day. What could possibly go wrong? We can observe over the weekend.
Yes, let's do them right now then. All right.
All right. Do you want to play some chess?
Huh. Okay, so they decided to play some chess. They look at the stuff. The suggestions were given to avoid that when the commit was checkpoint was happening, those sync replication were going to be immediately removed. So the suggestion was to have the WAL files written as fast as possible by disabling recycle off and init 0. And happily, they went to play some chess. Not just a Friday evening, they carry on playing the entire weekend. Both Monica and Derk beat the pride of Kevin, who lost all the matches. But between Derk and Monica, there was such a competition that they finished the weekend in a draw. They don't know what they were going to do about this. Maybe they will join the Postgres Chess League or chess team and start playing with other Postgres people that play chess. So after the weekend, they continue looking at these values. Those changes were super good. Finally, the WAL receiver could write as fast as possible, and it could sense the acknowledge of the commit message super fast, so that the SyncRep would accumulate, but not as fast as much as possible, and this message will be sent immediately back to the process that they were writing, and everything will continue working at normal speed, even when there was a lot of vacuum and checkpoints. And with this, we end this story of Monica DeBea until the next challenge. Thank you very much.